This is a recording for AQA Further Pure Mathematics, Matrices 5, where we're looking at the characteristic equation for eigenvectors and eigenvalues. Well, we met in a previous video that if M is a square matrix and V is a non-zero vector, if we had that MV was equal to a scalar multiple of V, then V is what we refer to as an eigenvector of M with a corresponding eigenvalue lambda. Now what we want to do is to develop a way of finding the eigenvectors and eigenvalues for a given matrix. We have the equation then that MV is equal to lambda V. To manipulate this any further, we need to realize that lambda V can be written as a matrix where we have lambda down the leading diagonals and zeros everywhere else multiplied by the column vector for V. Now this matrix here can then be written as lambda multiplied by a matrix with ones down the leading diagonal and a 0 multiplied by V. So in other words, lambda V is lambda I multiplied by V, where I is the identity matrix. Having got that idea, we can now subtract that from each side of this equation. So MV minus lambda IV must be equal to 0, the 0 vector. We can now factorize out of that the vector V, so we have that M minus lambda I multiplied by V must be equal to 0 vector. But we know that V itself is not 0 by definition. It's a non-zero vector that we have for the eigenvectors. This means that M minus lambda I, which is just a matrix, must be singular. It has no inverse. And by the definition of a singular matrix, that means that the determinant of M minus lambda I must be equal to 0. This equation, the determinant of M minus lambda I equal to 0, is what we refer to as the characteristic equation. And once we've got that, that allows us to work out an equation for lambda. And once we've got lambda, we can work out the eigenvectors. So let's look at that, first of all, neatly written out. So you see that we took the equation that we had from the definition of the idea of an eigenvector and manipulated to show that M minus lambda I must have no inverse and therefore is singular, and that gives us this equation, which is the characteristic equation. And I want to look at a couple of examples of this to show you how we use this equation to find the values of lambda. We're going to find the characteristic equation for each of two matrices. Firstly, a 2 by 2 matrix and then a 3 by 3. In each case, we're going to be using this equation. It says that the determinant of M minus lambda I must be equal to 0. So for the first one, the determinant will be equal to 1 minus lambda and then 2 and then negative 1 and 3 minus lambda. So notice the elements in there are just the elements from the matrix here, but minus lambda on the leading diagonal. And that must be equal to 0. Well, we can find the determinant in the usual way, so that we multiply the leading diagonal, 1 minus lambda multiplied by 3 minus lambda, and then subtract the product of the other diagonal. So subtracting negative 2 is plus 2. And that must be equal to 0. And multiplying that out, we get the following quadratic: lambda squared minus 4 lambda plus 5 is equal to 0. And this is the characteristic equation that we could then solve to find lambda. In the second case, it's a 3 by 3 matrix, but again the determinant will be the elements, but with 1 and then minus lambda. So we're going to subtract lambda from each of the elements in the leading diagonal. So it'd be 1 minus lambda, 2 minus lambda, and 1 minus lambda. But then all the other elements are just exactly the same as in the given matrix. And that's the determinant that we need to find. It must be equal to 0. So to work out the determinant, remember if you've got 3 by 3, we take the element in the first row, first column, 1 minus lambda, and multiply that by the determinant of matrix given by this part of the 3 by 3 matrix. So the determinant of 2 minus lambda, 1, negative 3, and 1 minus lambda. The next element in the first row is 0, so we can ignore that one. And then we get minus 1 multiplied by the determinant 3, 2 minus lambda, 2 minus 3. If you multiply that out, firstly that must be equal to 0. So then multiplying it out, that gives us 1 minus lambda, and multiplied by 2 minus lambda, multiplied by 1 minus lambda, and then minus negative 3, so plus 3, and then minus 1 multiplied by 3 minus negative 3 is negative 9, and then minus 2 multiplied by 2 minus lambda. And that must be equal to 0. Now you can see this is going to give us a cubic equation. So you can check through that. The cubic equation comes out to be minus lambda cubed plus 4 lambda squared minus 10 lambda plus 18 equal to 0. So in general then, when we've got a 2 by 2 matrix, we're going to end up with a quadratic characteristic equation, which means there will be two values of lambda, two eigenvalues, and hence two eigenvectors. And for a 3 by 3 matrix, we would expect to get a cubic equation, which will give us 3 eigenvalues and 3 eigenvectors in general. That concludes this video on finding the eigenvalue characteristic equation. In the next videos, we will look at how we then go on to find the eigenvalues and from that the eigenvectors.